All right, chapter 2, math practice problem set. You are asked to solve the following problem by constructing a line graph. In this problem, a scientist wishes to investigate the effect of temperature on the growth of Escherichia, I can never say this one, but it's E. coli bacteria found in the lower intestines of mammals. Her hypothesis states that if temperature and growth of E. coli are related, then the warmer the temperature, the greater the growth of the E. coli. The scientist sets up her experiment by using test tubes filled with nutrient solution and adds equal amounts of E. coli to each tube. She places each tube in a separate incubator or refrigerator so that the temperature varies for each tube. She allows the bacteria to grow for several hours, then measures the rate of growth in terms of doublings of the population size per hour. Create a line graph for this experiment by plotting the following data. Okay, so I'm going to do this. Boom. Create a line graph. That's the goal. Be sure to provide an appropriate scale on each axis. Place the correct variable on the labeled scale, so labeled axis, and draw a smooth curve through the data points. Line of best fit. So we're not like doing dot to dot. So a smooth curve would be the line of best fit right there. All right. So one of the things you got to find for each of your test tubes, there's 12 samples. The temperature goes from 10 degrees all the way to 48 degrees. And then we have doublings per hour. So you got to find your maximum doubling. Right. So we know that this graph needs to go at least to 3.0 doubling. And then our greatest temperature is 48 degrees and our lowest temperature is 10 degrees. And so when it says, where am I looking? Temperature and growth of E. coli are related. The warmer the temperature, the greater the growth. So growth over temperature. So number of test tubes isn't going to be graphed, but basically we can look at, we're going to put doublings over temperature, which is, X and Y, right? So always labeling axes. Temperature in degrees Celsius. So I always put the appropriate unit. My pencil's not that sharp. There we go. Leave a little room for some temperature markings. I'll sharpen my pencil. So the first thing I typically recommend, and when you are setting up scales, this is the hard part, is counting your boxes. 1, 2, 3, 4, 5, 10, 15, 22 boxes. So 22 boxes, and I have like 38 degrees here. So I want to know, what's going to use them, like, what is going to use the most area in my graph. I don't want to leave anything behind. We can go ahead and set this up. Hang on one second. Okay, so as I was saying, we can set this up with a little bit of guess and check. So we could do the 5s. Let's see if we get 10, 20, or was I 10, 20, 30, 40. Well, we have to have up to 50. So that by 5s isn't going to work. Or using 5, each one of these would be 2 degrees. What about 2.5? So let's try this with this being 10, 20, 30, 40, 50. So we can fit the temperature within those. So this would be 10. So start out with 0 degrees, 20, 30, 40, 50. They don't really give us enough room here. I'm going to say temperature in degrees Celsius. It should have been a little bit higher up. Okay, and then on this side, we've got doublings per hour. Okay, so let's say go from 0, and then 1, 2, 3, 4, maybe. Give it a guess and check. Mm, Gotta get at least 3 of them on there. So 1, 2, 3. Oh, that doesn't use very much of our space. If we go 0.5. What if we do the same thing actually? Let's do the 2.5. Well, that doesn't, that doesn't make sense. So go 5, 1, 1.5, because we gotta go all the way to 3, 2, 2.5. Okay, that's not enough. Awkward. Awkward distance on here, that's for sure. Three. 1, 2, 3, 4, 5. 2, 3. I guess. Maybe let's try 6, which is kind of weird. 1, 2, that'd be 0.5, 1, 2, 3. So 1, 5, 2, 1. Nope, 6. Whoops. Sorry, a little guess and check for me. You might have a more efficient way to do it, but these are just kind of strange intervals, and I'm trying to use all the space that we possibly can to make it work best. And I guess you could cut a little bit out of each side of it too. So 0.5. We kind of have these 0.5 increments. That's going to be the easiest. 1.5, 2.5. 3 is our highest. I don't know. I'm not convinced, but we're going to go ahead and graph this. Okay, so on this side, what we have is doublings per hour. Right? Okay. And then overall, we have to give it a name. And typically we are going to say like the y-axis over the x-axis. And that's like our title. So it's going to be like something really silly. Doublings per hour of, what are we measuring here? Of E. coli at various, let's say, at various known temperatures. Something that tells me a little bit about what's being studied, okay? Hopefully you can see that okay. You can put it up here if you want to. But basically, when you title a graph, you just take the y-axis and the x-axis and you create a name with it, and make sure that you tell what you're, like somewhere in there, like what's actually being measured. So let's get to it. Test tube number 1 at 10 degrees. And we got 0.2. Oh gosh. Okay. This would be 0.25. I don't know. It's a third of 0.5. This is like a terrible, terrible interval. I don't know, you guys. I think I'm just gonna go with the goodness, terrible interval. Okay, 0.5 divided by 3. So each one of these is like 1.6. A little bit above that. Whoops, a little bit above that, right? And remember, we are just doing the estimate on the curve, so it shouldn't be too bad. We got 15 and somewhere in here, 2.5-ish, 0.3. Well, 2 of those, that'd be easy, huh? Because they're like 0.16. So that works out. 15. Temperature, at 15 degrees, there are 0.4 doublings. So a third of the way up to that, or 2/3 of the way up. 20. We get 1 doubling. So now we're starting to see some change in the growth. 25, 22-ish. 1.2, so a little bit above that. It's like super awkward. I hope you can find better intervals for this. But really we're just going for that curve. At 25 degrees, we've got 1.5. Oh, thank goodness. Right on the grid. Super easy. 30, 2.2. Halfway betweeners-ish, a little bit below that. 35. Obviously, it'd be easier on different graph paper. You're welcome to do it if you'd like to on a different piece of graph paper. What was this one? 35, 2.8. Would that be 2.66, 2 point ish? Yeah, it's actually like closer to that right there. I just doing my little fractional math. Don't get confused. Just get different graph paper. That's my 35, 38-ish, 7.5. Can round up. Then that's going to be my top at 3. And then we're going to come back down 2.8, the same number. So I'm going to be like, okay, let's graph in the same spot. 45 degrees at 0.1, graph over. And then 48 degrees at 0.2. All right, so there is the graph. And then my curve, just going to, whoops. Okay, and one thing I like to do, I like to make them color, especially align the best fit, shows the trend line. Not too perfect, but that's definitely what we're looking at. I think it would look a lot better on a different piece of graph paper. So you're welcome to do that, but that's the graphing part of things. Provide an appropriate title for this graph. Voila, see above. Identify the independent variable. The independent variable is the one that is controlled by the experimenter. So this would be, you have to fill in the blank. Identify the dependent variable. This is the one that is measuring. It's the outcome. It's the one that's kind of all over the place. Well, okay, so independent variable, controlled, and dependent variable. This causes that. All right. Identify the optimum temperature. So we're looking at 38 degrees Celsius. I think that's right around body temperature, peeps. Surprise, surprise, right? Okay. And then solve the following problems using dimensional analysis. Be sure you set up your problems so that the units cancel. This stuff ought to look familiar. We're going back to the same problem setup that we were before. The speed limit on the highway in Canada is 100 kilometers per hour. You're given, that's a fraction, but that's what you're given. 1 kilometer is equal to 0.62 miles. Okay, so there's another equivalency there. Calculate the speed in miles per hour. So you're converting. You're given 100 kilometers per hour and asked to go to miles per hour. So now we know we've got 1 kilometer, and that's going to give us 0.62 miles. Bing, bada bing, cancel out. Multiply across the top. And then we just move our decimal, boom, boom, right? So 62 miles per hour. Pretty self-explanatory. How many centimeters exactly are in 1 yard? Gives you 1 inch, is 2.54 centimeters. Do you remember how many inches are in a yard? I hope so, 3 feet. So we're looking at, it just gives us in a yard, right? So what we are given in this case is 36 inches. 1 inch equals 2.54 centimeters. Boom, boom. I have no idea. Ooh, 56.7. 1, 2, 3. We'll go. We got 3 sig figs there. Oh, we have to talk about that. We got to talk about sig figs. All right. Boom, boom, boom. A power plant burns 12 tons of coal per day to generate electricity. 12 tons per day. We got a fraction. Each ton of coal produces 7,327 kilowatts of electricity and emits 0.75 pounds of CO2 per kilowatt. How many tons of CO2 are emitted each day? Round to the nearest ton. All right. So we start off with, we're given that there's 12 tons of coal being burned a day, and we're being asked to answer how many tons of CO2 are emitted each day. So you don't necessarily need to say per day because the whole conversion is going to be per day. So we're going to start off with 12 tons of coal. This per day and this per day we know is going to stay. This makes it a little easier. And you can put it over per day, but that per day is going to stay. All right. So we know that we've got 1 ton of coal. Here, oops, I should have highlighted that. So each ton, so it's 1 ton for 7,327 kilowatt hours of electricity, which we'll cover later, like how to really break down that unit and what it actually means. And then 1 kilowatt hour produces 0.75 pounds of CO2. Whoops. Okay, so how many tons of CO2 are being emitted each day? And then you need to know that 2,000 pounds is 1 ton. It's not given to you anywhere here. So this is just like something you would have to Google. Like, what do you know about units? 2,000 pounds is 1 ton. Okay, so now we should be where we need to be. So we've got tons of coal, 1 ton of coal. Oh, sorry, CO2 and CO2, because those tons are different, right? So we got tons of coal, gives us this much power, and then here's our power conversion there. This is why it converts, right? Because we can look at the power, and then power, this production of power produces the 0.75 pounds per coal of CO2, sorry. So in this case, we're going to multiply, and then that will give us a value, and we would divide that value by 2,000. So I'm just going to say, take this number, 12, multiply, divide. And it works the same. Okay, I can hit equals. That would be my value, but I know I'm just going to divide that by 2,000 anyways. So I just skip a step that way. 32. 0.9, but I only have 9,751. Okay, whoops. I got how many significant figures in this problem? I'm looking at 0.75, so I have to round up. 33 tons. Whoop. CO2. There we go. Trying to hurry. Sorry about that. Okay, and then we've got number 2. The tropical rainforests are being cleared at a rate of 8 million hectare per year. Hectare is an measure of area. How many football fields per hour are being deforested? 1 hectare is equal to 2.47 acres, and there are 1.32 acres in a football field. So 1 hectare, 1 acre per football field, and this is per year. So I'm given this rate, 8 million. I'm going to say 8 times 10 to the 6th hectare. The same thing, and you're going to learn to be really flexible with changing out million to 10 to the 6th. So 8 million hectares per year. And then that year is going to stay, right? So let's go to the hectare. 2.47 acre. And then we've got 1.32 acres in a football field. I don't really know why that's like irrelevant. I guess it's more like so that you could visualize it. Right, so the same thing. We're gonna multiply, and then divide. So 8. Easier to just put in zeros on that one. 6 zeros times 2.47 divided by 1.32. Okay, and then I've got 1, 2, 3, 4, 5, 6, 7. 1 point. I've got 1 significant figure, right? Because I only have 8 million. It only gives me the 1 significant figure. Oh, I gotta do time. I forgot about that because I'm supposed to go till it's like per day. What does it say? How many football fields per hour? Oh my goodness. Okay. Well, let me talk to you about something. Sometimes you can do this in 2 steps. So this is going to give us per year. 1 point, but don't do any rounding. Keep those numbers the same. Oh boy, that's like ridiculous. 4, 9, 6, 9, 6. Oh, repeating 9, 6. Okay, it just repeats. Times 10 to the 7th football fields per year, right? Okay, so here's where we're going to start off. We'll take what's on that calculator so that there's some more, it's as accurate as it can be, right? Football fields per year. And now we're going to say, I guess if we're rounding, technically this should round to 9.7. Go ahead and do that. I'm looking, because it's repeating, round to 9.7, just for fun, just to be more accurate. Okay, so we're supposed to go to an hour. 1 year is, we can do this a couple of different ways. We can do 365 days, or you can do 52 weeks, depending on kind of like what you want to do math wise. All right. I think the answer on here, yeah, let me flip back. The answer on mine is actually given or is set up with weeks. But there's two, you know, like I said, it's your choice. You can do 365 days. Easiest, I think. And then 1 day is 24 hours. So bing, 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 and then we got football fields per hour. So we're going to take 1.496969 and divide that by 365 and divide that number by 24, which gives us a teeny tiny little, oh, I didn't put it in millions, did I? 1, 4, 9, 9, 6, 9, 7, 1, 2, 3, 4, 5, 6, 7. Okay. Well, no, that wouldn't work. Now take this number, divide by 365 and divide that by 24. Well, I'm glad I caught my own mistake. So we've got approximately 17,000 football fields. If you want to be technical, we can put 1709. And we really only start off with like the 1 sig fig, but we're not going to say 2,000. We need to be, yeah, a little more detailed. Oh, it says round to the nearest acre. Nearest acre. Well, that would be it, right? There's acre per hour. Oh, it's a good thing I modeled reading, rereading the question. But that's really what I need to do, kind of get lost in the weeds. Sometimes like solving through these problems, and then you're like, oh, what exactly was it asking? And you need to return to the question and make sure it's how many football fields per hour. So I got football fields, and I do have hours in here. That is my target, right? And I should be rounding to the nearest acre because that's what the directions say to do. So read the question before, go through, annotate if it is necessary for you, but always go back and reread your question and make sure you're answering things correctly, especially when it's a weekend and you're super tired and you have a headache and your name is Mrs. Bader. Anyways, I really hope that was helpful, and that I can get this uploaded for you. Alrighty, bye guys.